Dear students, welcome to the fourth week of our offshore production engineering course. Let me pass through to our topics. In the first week, as you remember, we gave a short, brief introduction and information about the course, and in the second week historical background of geology and reservoir of oil and gas, and in the third week, offshore oil and gas operations we mentioned about, and now ocean environment and sea states we will mention about. It will include the meteorology, wave, current, tides, sea ice, and seabed soil topics inside. Alright, let's go on. Okay, I will mention about the ocean environment and sea states in here. Uh, Working in offshore, as we already know, all of us, working in offshore is more complex than working in onshore environment. So this extra dimension of complexity is created by the environment itself. So the ocean environment, which comprises the meteorological and oceanographic data other than earthquake environmental conditions, it affects everything in offshore, actually offshore situation, from the design of the offshore platforms, starting from the design of the offshore platforms, the submarine pipelines and terminals, to the planning, installation, and maintenance procedures. So, experienced specialists working in this area are generally consulted while defining the pertinent meteorological and oceanographic conditions affecting a platform site. So, the level of the oceanographic and meteorological information needed during the design and the installation of the platform depends on the amount of the knowledge which already available concerning the platform site and its general surroundings. So normal or operating the meteorological and oceanographic environmental conditions, including the harsh conditions as well, which are expected to occur frequently during the life of the structure, are needed to plan the field operations, such as the installation, and to develop the operational environment load. Extreme environmental conditions, defined as those conditions which recur with a return period of typically we say 100 years. Okay, so they are needed to develop the extreme environmental load. Okay, so if we talk about the meteorology is the science that concerned with the atmospheric phenomena, especially in relation to weather and the climate. Okay, so broadly, it is concerned with the observation of the weather elements. From this, the observation of the weather elements, the communication of the observations to forecast centers, the analysis of the observations using available techniques, the preparation of forecasts of weather and sea conditions, the analysis of the forecasted conditions on offshore operations, and the communication of forecasts and the operational recommendations included. The preparation of the climatological studies also included this. Okay. Hence, what we can say in a nutshell, it deals with the weather to a large extent and with the climate and monsoon to a lesser extent actually. So the weather itself is defined as the state of the atmosphere at a specific time with respect to heat or cold. Okay, heat or cold. So wetness or dryness also affecting this one, calm or stormy weather or clearness or cloudiness. So these type of things are affecting the description of the weather that you are making. So often the term is used to identify the rainstorm and other unfavorable atmospheric conditions actually in offshore environments. Okay. So another one is the climate. Climate is defined as the average course or condition of the weather in a given area over a period of years as exhibited by temperature, wind, the velocity, and precipitation itself. Right? So the climate is spoken of as being hot, cold, wet, or dry, we describe, right? So sometimes it's referred to as harsh conditions or mild conditions. You will see this type of terms as well in offshore environment. A basic relationship exists between climate and the latitude. Latitude means distance north or south of the equator. That's the distance, alright. So according to this, also it can be classified as well. Okay. So because offshore drilling crews usually stay in one region during a drilling operation, changes in climate rarely affect them. So until they move there is a marine vessel, for example, and there is a movement needed, it takes place from one part of the world to another part, so there can be some needed to be moved. So because of that, they can be affected during this transportation process, right? So on the other hand, what we can say, the changes in the weather often occur in minutes or hours as rapid moving weather systems approach as a pass a given point. Right? So even though in certain areas of the world the weather can change radically in a short span of several hours, for example, it's often possible to predict the sudden weather change to the hour as much as 24 hours in advance. So, since meteorology or weather is concerned with atmosphere, let us discuss what atmosphere is and how air, or for what matter, wind plays a big role in generation of weather elements. So, we have to discuss this one first. So, let's move and start with the atmosphere. Okay? The atmosphere of Earth is defined as a layer of gases surrounding the planet that is retained by the Earth's gravity. So the atmosphere protects the life on Earth by absorbing the ultraviolet solar radiation, warming the surface through heat retention. We call it greenhouse effects, right? So and reducing the temperature extremes between day and night, and the diurnal temperature variation as well. So the common name given to the atmospheric gases used in breathing and photosynthesis is what we all know this one, it's air, right? So dry air contains about 78% of nitrogen by volume and 21% of oxygen by volume again, and about 0.95% argon, 0.04% of the carbon dioxide, and some small amounts of other gases included as well. Air also contains water vapor, on average around 1% at sea level and 0.4% over the entire atmosphere. Right? So Earth atmosphere can be divided into four primary layers. You can see here in the five, but in most resources we can see that it given in four different layers. So troposphere, the first one is between 0 to 12 kilometers thickness, and then stratosphere is 12 to 50 kilometers, and the ozone layer in this part in the stratosphere you will find the ozone layer that we are describing. Mesosphere is between 50 to 80 kilometers, and from 80 kilometers to 700 kilometers, thermosphere we call. After thermosphere section, above 700 kilometers to more than 700 kilometers, we can say exosphere, right? So there is another layers we called Karman layer line in here in 100 kilometer around and above 700 to 1200, I think 12,000, sorry. It's exo-base. There's another layer. There are three different layers. Which is the closest one is the ozone layer to the Earth. All right. Okay. So although the air content is atmospheric pressure vary at different layers, air suitable for the survival of the terrestrial plants and terrestrial animals currently is only known to be found in Earth's troposphere. Okay. Okay. So after this generic information, we can continue by giving some more information regarding the atmosphere. So when the surface of the Earth is heated due to the radiation of the sun, called insolation, it in turn heats the air above it, right? And the anechoic heating of the Earth causes the air in the atmosphere to be heated unequally. Okay, this happens. And the differential heating of the Earth is caused by the angle at which its sun rays strike the Earth's surface and the varying capability of the regions of the Earth to absorb the heat. Okay, so land surfaces have faster rates of heating and cooling than do the water surfaces does. So that's the unequal heating. There's an unequal heating is happening. It's not a kind of equal distributed heating all over the world. So uh, because of the reflections from the ground, okay, it can be water, sea, lakes, whatever, or a continent, all right, land. So the reflections are different. So because of that, there is an unequal heating of the atmosphere. It results, all right. So what happens as a result of that? In a mixture of warm and cool air, it's happening from region to region, right? And it's dynamic, it's moving, right? So warm air in the atmosphere expands and become less dense and rises. And then cool air contracts, become more dense and moves downward, right? So warm air lying over cool air will eventually cool and move downward, and the new warm air will replace it. Okay? So the warm and cool air in the atmosphere exert pressure over the surface of the Earth, which is known as the atmospheric pressure. Okay, we call it atmospheric pressure. Okay, don't forget. So in the low pressure area is formed by the warm air expanding and rising in the atmosphere. And the high pressure area is formed by the cool air contacting and moving downward in the atmosphere. Right? So the rotation of the Earth causes these low and high pressure areas to move and circulate. This circulation of air is responsible for the creation of the wind and other weather phenomena that's occurring and we are seeing all over the world, right? Okay, so let's move to the wind. Okay, what about the wind? So horizontal movement of air in the Earth's atmosphere is known as wind. We already know this one, right? Other than heating and cooling of the atmosphere, there is also another factor we call it Coriolis force. Coriolis force, which is simultaneously responsible for producing the prevailing winds. So as you can see from the picture, okay, in the figure, the prevailing winds, also known as the surface winds, can be measured at the surface observing stations. Okay, we can measure it today in all over the world. Okay, by using the surface observing stations. Okay, but it's important to note that in here the wind direction is always reported as from. We use from. All right, wind direction. When you see from the word, it gives you the wind direction. For example, a northeast wind indicates it blows from the northeast. A southeast wind means it blows from the southeast direction, right? You have to record this one. So when you are in offshore environment, so you will face with this type of terminology. So you have to get bit familiar with this type of terminology. So because of that, I'm giving this. Okay, similarly, it also is to be noted that the wind speed is conventionally reported in knots. Knots. So one knot equals to 1 nautical mile per hour, and it equals to 1.15 statute mil, right? Statute mil per hour, and it is 1.852 kilometer per hour. So wind speeds are categorized as Beaufort numbers. Okay, Beaufort numbers. This is a kind of index number which has been developed. It's the range of that is between 0 to 12. All right. So let me give some more explanation regarding on that. In the summer months, for example, the warm winds reverse and travel back over the oceans and meeting low pressure air on land. So the low pressure air is intensified by contact with the warm air, right? And summer monsoons are usually characterized by heavy rainfalls and are sometimes referred to as wet monsoons, right? So high humidity and large differences in temperature between surrounding oceans may cause a kind of monsoon fog to occur. And, and in a kind of offshore environment, you will face with this type of this type of foggy weather, which resulted by the monsoon, right? So, so what we can say, monsoons have little or no effect in polar regions and in areas surrounding the equator because temperatures of the land and water are almost similar in these type of areas, right? Almost similar. So because of that, you cannot see any difference. But in regions like for example, in our country, like in North Hemisphere, um you are familiar to see the foggy weather, especially in the offshore environment. Right? So monsoons are common in South Asia, northern Australia, North and South America, and parts of Africa, and the greatest monsoons occur in southern and southeastern Asia. We have to be aware of. So what about the Beaufort wind scale? Okay, as you can see here, the Beaufort wind scale with the corresponding sea state codes. And Beaufort numbers has been given from between 0 to 12. What it means, the 0 is the calm weather with the sea surface smooth and the mirror-like, okay, calm and glassy, alright? So when you go, for example, let's go to the 6. The 6 is strong breeze, it has larger waves, white caps, common, more spray, right? 5 moderate waves, taking longer form, many white caps, some spray, can be seen. When it goes through the harsher conditions that you can, as you can see here in the 12, for example, you see hurricane, okay, air filled with foam, and this type of it's very harsh conditions you can see. So wind velocity in this category is more than 64 knots. Right? Okay, after giving this example, you will face with this one a lot. You will face with this one a lot when you go to offshore environment. So it's I think it's kind of essential information for you. It will be in your future. So the major factor in the let's talk about the weather phenomenon, by the way. All right, for the weather phenomenon, the major factor in the development of the weather is air masses. Okay, air masses. So air masses are the bodies of air that remain for the extended periods of time over large land and sea areas. Usually these areas are around 1,600 km or more across, all right, with uniform heating and cooling properties. Okay. So in the figure here, you can see actually the lowercase c and m, as you can see here, the lowercase in the beginning, m's, and c's you can see, right? It's clear, right? C, m, as you can see, right? So these lower cases refers to the continental and the maritime air masses developing over land areas and water areas, respectively. Okay, and there's a big capitals in here, as you can see, T, P, right? T, P, E, as you can see, right? These type of letters refers to the Arctic, polar, and tropical air masses development over the poles, upper latitudes, for example, cold regions, and low latitudes, the warm regions, respectively. Okay, from upper to lower latitudes, there is a movement. All right, there will be a movement. Which one is the upper one? Which one is the lower one? It describes this. Right? Okay, so thus, for example, the CP. Let's talk about the CP in here. For example, as you can see, CP refers to the continental polar air mass source region, and MT, for example, MT refers to maritime tropical air mass source region. Right? So these differential air mass source regions have different temperatures and moisture content. So for example, the tropical air masses resulting from the heating of land surface, CT, okay, okay, heating of land surfaces, have high temperature and low water vapor content. Okay, and the temperature and low water vapor content, so then I call it CT. All right. Whereas, for example, maritime air masses called MT. One example you can see in the Aegean region. Okay, it means that it has a lower temperature and much higher water vapor content. All right. So it is this water vapor content in the air masses that contributes to the energy that produces hazardous weather like frontal storms, thunderstorms, hurricanes, or related disturbances. So whenever two air masses meet, a front is formed. Okay, front is formed. What is the front? So fronts are the surfaces of the discontinuity or interfaces between unlike masses of air. Right? We can describe. So fronts occur when masses of warm and cold air, such as we referred in the previous section as MT, right, or MP. So when they meet, right. So the change in the temperature and humidity and cloud formation and wind speed and the direction occurs. So fronts are associated with most of the severe weather conditions on Earth actually. So there are mainly four types of fronts we know. These are cold fronts, warm fronts, and stationary fronts. Also the occluded fronts included. So a cold front exists when the cold replaces the warming. Okay, it means that when cold replaces the warming, so we can say that there's a cold front exists. Right? So as you can see in here in the figure, the cross section of fronts, A is a kind of example for the cold front. B is the warm front example. In the A, for example, what's going on? The direction of the frontal movement in the below section is coming, and the upper part is advancing cold air behind the cold front. And cold front map symbol, as you can see in the lower part. And what's going on? The float development because of frontal lifting of the warm moist air to the upward direction. So receiving warm air ahead of the cloud front is going directly to the upward direction, and the cloud forming happening. So A. So we can say this one is a cold front example. Okay. So for the B, as you can see, warm front map symbol is in this part, as you can see in the section. The direction of the frontal movement in the below section can be seen here. And then advancing warm air behind the warm front is going to the upward direction. And again, cloud development you can see here, all right, because of the front of the lifting of the warm moist air, right? So receding cold air ahead of warm front also, as you can see in this area. So this is an example for the warm front section. Okay, the reverse direction actually, the warm front section you can see, right? So another one is the cold type occluded front, and what's going on in here, as you can see, B and A. So A and B in the from the upper view. Also A and B you can see here, and A and B. What's going on? There's a occluded front. There's a occluded front which prevents air to be moved from one section to another. All right. So it's a generic example for the occluded front in here. So a warm front exists when warm air replaces the cold air, basically. Winds are usually less violent in warm fronts than in cold fronts, and precipitation is in the form of the showers or drizzle. Right? So warm fronts usually move more slowly than the cold fronts. And the stationary front, what about the stationary front? In the third section, stationary front is a discontinuity or zone between the two adjacent air masses that's not moving or it's moving a little. Okay? The typical situation is one in which poor weather conditions resembling a warm front persists. Right? So, and in the occluded front, which you see in the sea, right, is formed when cold front overtakes a warm front, lifting the warm air above the Earth's surface. Okay, so three types of mainly the three different types of occluded fronts are generally identified, which are determined by the coldness of the air replacing the original cold front regarding the air ahead of the warm or stationary front. Right? So these are cold occlusion, warm occlusion, and the neutral occlusion we described. For example, in the cold occlusion occurs when the coldest air is behind the cold front and the warm front is forced aloft. Right? So warm occlusion, the second one, occurs when the coldest air is in the ahead of the warm front and the cold front is forced aloft as well. So the reverse direction. So what's happening in the neutral one, in the neutral occlusion, it occurs when the temperatures of the cold air masses of the cold and warm fronts are the same. Okay, we call it neutral occlusion. Okay, let's move. So when the interface between cold and warm air masses becomes unstable, in the case, for example, when the polar easterlies and the westerlies converge or plunge down, okay, it can be happen as a result of the effect of the friction and the differences between the densities of two air streams. A wave-like from pattern is created, as you can see in the figure here. Air mass source regions, different types of them. All right. So it can be clearly seen in here. So low pressure develops at the crest of the uh, develops at the crest of the line, as you can see, right? Okay. Wait, sorry. Okay. So a storm with winds of, for example, 65 knots, we called what we said. We said the Beaufort number we called is 12, right? Very strong one. Okay. So its greater is known as a tropical cyclone, right? Tropical cyclone. Owing to the lack of the great contrast in temperature, the tropical cyclone tends to be less specific in size, shape, and the wind system as well. So nevertheless, over the tropical oceans, relatively small and consequently extremely intense cyclones do develop. So um, these are variously called hurricanes, typhoons, and so on. For example, a tropical cyclone is the universal term for what is known as a hurricane, right? In the North Atlantic, for example, in the Caribbean Sea, you can see this, and in the Gulf of Mexico, you can see this. The Eastern Pacific and the Central Pacific, you can see this. And other regional names for the tropical cyclones include the cordonazo, for example. They call it the cordonazo. I had one Mexican friend and they were calling it as cordonazo. And in Australia, for example, they were saying it's different. They were saying Billy Billy, or Billy Billy, they were saying. So, what's going on when you go in different locations and different traditions, different cultures? You will see different names of these as well. So you have to get familiar with these by time it will be offshore. But if you go to an offshore field, for example, in Australia, when they say the willy willy, so it means that there's a tornado is coming, hurricane is coming on the way, right? So with the 12 before number 12. Yeah. All right. So I will talk about the oceanography. I will talk about a little bit about the oceanography and sea life and sea creatures and how we can prevent what's our responsibilities for the sea creatures and sea environment according to the sea environment when we are working in the offshore environment. We are doing an offshore work, offshore drilling, offshore production in each stage of them. So we have to be responsible and we have to be very careful. We have to take care of the nature itself. So, oceanography mainly is concerned with the prediction of the wave and swell conditions from the forecast wind conditions or the determination of the past wave and swell conditions from known past wind or pressure conditions. Okay. Concurrently, the ocean current and tide are also a matter of concern for oceanographers in higher latitudes, and the sea ice is also an added parameter for calculating its effect on offshore structure. Right? Offshore structure for what? For which information is also required to be there, right? So we have to be responsible and we have to work with the oceanographers before starting to in the offshore environment. We have to work with the oceanographers. This is a must, right? And they have to evaluate the sea level, seabed, and the conditions and the nature living in there. So we have to describe firstly. We have to be responsible to the environment, and then we decide where we will drill, where we will put our fields, where we will locate our wells. In most conditions, nobody is caring about this one. If there's an oil and it's profitable, they directly start to mention about the locations of the well. But before that, what's need to be done, they really need to consider the environment. There can be for example, species which already has some problems and their species is exhausted maybe. So then there's a need to be care about this actually, right? Okay, so for the ocean waves, they may be formed by the several forces, including the frictional contact between wind and the ocean. Okay, so there are two parameters in here in the offshore environment: the wind and the ocean. Okay, this we need to be care about, right? And in the tidal attraction of the sun and the moon and the vibration of the earth as well. So wind waves are formed by the contact of the wind with an ocean surface and have the single greatest effect on offshore operations, right? So, so for example, let's talk about the wind waves. Wind waves are formed. Wind waves are formed by the contact of wind with an ocean surface and have the single greatest effect on the offshore operations. Right? So as wind blows over an ocean, friction exists between the wind and the ocean surface. So the energy transferred from the wind to water, right? Via the friction results in the motion of the ocean surface itself. Okay? So wind energy is transferred to only the very top surface of the water, to the top layer of the water, imparts energy to the water directly beneath it, and so on. Okay, so the energy decreasing as the process of the proceeds. Right? So this transfer of energy through the friction causes wind waves to form. So the wind waves develop and grow where a certain wind prevails from the same direction for a period of time. So this area of wave development is called the fetch. Right? We call it fetch boundary. Okay, as you can see, the fetch boundary, this part. Okay, so the fetch is also defined as the distance over which the wind blows to generate the observed waves at a given position or point. Right? A fetch may be hundreds of miles long, if it's possible. Maximum wave heights exist at the leeward or downwind direction, so the boundary of the fetch. Okay? Waves are still in their fetch under the influence of its wind. They call it sea. Okay, if there's effect of the wind still you can see, so we call it sea. If it is not, right, in the fetch boundary, if it is not, then we call it swell. Right, waves that have moved out of their fetch and into the weaker winds, as you can see here, so we call it swell. Right, swell. So swell decreases in height and has regular movement actually. So in comparison to the sea, which appears choppy, for example, swell appears around top. Okay, so I think this is a good explanation regarding on what you will see in the offshore environment uh, in sea line. So we call it fetch. Don't forget fetch, right? Let's move. Okay, the tidal waves, also the tidal waves, are caused by the action of the sun and the moon on the oceans of the earth. Right? So they have the longest wave periods of all, some lasting for over 24 hours, right? So the tidal waves travel at speeds of approximately 400 knots, and tsunamis or seismic sea waves, often confused with tidal waves, is happening. They are produced by submarine earthquakes or explosions. They are different, right? So when a seismic disruption occurs, great volumes of water are displaced, transferring the energy. Why? So the reason is transferring the energy from the ocean floor through to the surface, through to the fetch area in here, as you can see in this area. Alright, and it's suddenly disturbed. When this suddenly disturbing happens, so a volume is moving, it creates a big wave. It creates a big wave. Alright, but this is totally different thing. We cannot compare with this phenomena that I am talking in here. Right? Alright, so this is totally different. So this energy transfer results in huge breakers that inundate the shoreline, destroying the boats and installations in most of the things. Okay, so tsunamis are virtually unnoticeable in deep water. You cannot notice it. They have deep water wave heights of approximately 3 feet, right? The wavelengths of hundreds of miles and the wave periods of 15 to 60 minutes. So it becomes harmful when it reaches to the land. Okay, in the offshore environment, if even if you are closing to the fault and the location of the earthquake happen, exact location, so you cannot feel too much, not too much, right? Okay, so it means if the height of that is approximately 3 feet, it means that around 1 meter, nothing, right? But when it goes, it becomes bigger and bigger when it goes by time, and it becomes far away as a circle, far away from the center of the earthquake. When it's far away and reaches to the land, through to the land, so it creates a kind of energy. It starts to show its energy, right? So when it reaches to the land, of course, it becomes very destructive and harmful for people's life and buildings and etc. and other things. Okay, so we have to be very careful for the tsunamis. But this is totally different thing when you compare with this normal situation, the fetch boundary. Okay, the tsunamis and other things are abnormal. It's not a normal thing. It's nature, but it's not a normal thing. You cannot classify this as a kind of inside the fetch, right? Okay, so the wave description I will give in here, the wave description. The wind is generated, the wind generates the waves are mostly known as the surface gravity waves, right? So for its description, let us consider a waveform that is a simple harmonic, so that at any time it has a sinusoidal shape as shown in the figure, as you can see, sinusoidal shape. For this shape, you are already familiar with this shape. Where you are familiar in the reservoir, we are seeing these structures as well, right? This sinusoidal, as a result of the folding, what's happening? It's anticline and syncline, right? Remember, in the upper parts, we call it anticline, and there can be some trap in here. It gives us the opportunity to have a trap for the oil and gas, right? So in the syncline, the reverse action. So the same behavior we are seeing here, kind of kind of sinusoidal way, sinusoidal behavior we are seeing in the waves behavior as well, say, okay, in terms of shape. So for its description, we let us consider a waveform that's simple for harmonic, okay, sinusoidal. So in here, the wave height h, we call it h, is measured from the crest, the top of the wave, to the true, to the lowest point of the water surface level between the crests. Okay, so the heights of the wind waves rarely exceed 55 feet. 55 means nearly 20, 15 to 20 meters, but they have been known to exceed the 100 feet in most times. 100 feet, nearly 30 meters. Right? So wave heights and the sea characteristics can be reported in terms of the what we mentioned. We learned that before scale, right? In the previous table, remember before scale. I will give that table to you, so you will not have any problem with this one when you are classifying. And the scale range from what? We remember default numbers 0 to 12, right? 0 was indicating the calm, mirror like sea with no waves. There's no wave. And when it reached to the 12, it's indicating a height of more than 45 feet, 15 meters waves at a sea that's completely wide with blowing foam and spray, right? Okay, so after giving this example to you, let's move. So let's just describe the parameters in here. There's A and B points, the top points of the two waves, okay, two sinusoidal top points, and in the below there's a wave tool in here in the lower part. There's a wavelength we go from A to B here, and the wave height, it starts from the highest point to the lowest point of the wave itself. Okay, as you can see. So the calm sea level, can you see? You can see here the calm sea level as 0 in here. Okay, this true length region and crest length region, when you are the region that's upper of the calm sea level, the level that's below the calm sea level here. All right. So the ocean bottom is described in here, and the direction of travel has been given in the according true to the right direction. Right? True to the right direction. Okay. So in this case, there are four factors we have to be care about. Okay, for the creation of the wave. So one of them is the wind speed, the duration, the fetch. We already mentioned the fetch, and the water depth. Okay. So these four factors determines the wave height. Okay, wind speed, duration, fetch, and the water depth. So the wind speed is the most important one, according to this, compared with all of these, right? The faster or the strongest the wind blows, the higher the waves will be, although the wind speed affects the wave height only up to a certain extent, actually. So the duration of the wind speed means that the longer the strong wind blows, the higher the waves will be, okay? So for example, if let's talk about a 30 knot wind, believe, over an area of unlimited fetch, for 5 hours. Okay, so this will create nearly 7.5 feet waves, two and a half meter waves can develop. But if that same 30 knot wind blew over the same area for water for 30 hours instead of 5 hours, 30 hours, the waves will reach up to 16 feet, more than 5 meters. Okay, so similarly, the longer the fetch, the higher are the waves. So for example, let me give another example. If a 35 knot wind was blowing across a 1 mile area, 1.6 kilometer, let's call it short fetch, not unlimited fetch, we call it short fetch, the waves might reach only 2 feet in height, 2 feet less than 1 meter. So if that same 35 knot wind blew across an area with unlimited fetch, the waves at least 30 feet in height, with 10 meters in height, would eventually develop. So the water depth is significantly on the shallow seas, right? And bays as well. So where the shallowness causes waves to be relatively slow. So in an open ocean, in the offshore environment that we are talking, the water depth is sufficient for the maximum wave development. So you have to be careful in the offshore environment when you are working in the offshore environment, offshore rigs, all right, in oil and gas industry. So you have to be very careful about these parameters and what's going on around you. You have to be familiar with what's going on around you, right? Okay, let's go with the wave description. So there's a very important parameter we call the wavelength, lambda. Parameter is lambda. Right? This is defined as a horizontal distance between two successive wave truths or crests. Right? So the wind waves of the surface gravity waves have wavelengths that are usually 12 to 35 times of wave heights. Right? So the waves in the swell have wavelengths that are 35 to 200 times their height. Okay? So the amplitude, the A, we call it A, is a measurement of the vertical distance from the wave axis or the still water level at the top of the wave peaks, crest, at the bottom of the wave trough. So depending on the type of the wave height, we call H, okay, may be equal to twice of the amplitude, H equals to 2A, let's say, or may not. So because in certain wave crest, amplitude can be greater than the true amplitude. So the wave period T, right, wave period T is the time interval between the passage of two successive wave trough or crests. So this can be determined by measuring the time taken by the two peaks to pass a certain point. Okay. Okay. So we are coming to the end. So before finalizing, I will describe two more. Okay. Frequency, one of them. One of them. So the parameter we described it as f or omega, right? Of the wave is a measurement of how often a wave recurs in a measured amount of time, right? So one completion of the repeating pattern is called cycle. Cycle, okay? This is a one cycle, but starting from here through to here, it's a one cycle. Okay? So the frequencies of the progressive waves or those that move forward indicate how fast the waves move forward in units of cycles per minute, right? So the wave frequency is related to the wave period by period. Right? So most wind waves have short wave periods, starting from the 3 to 30 seconds maybe. So the wave interference is caused when the sea of swell converge. Right? So the irregular waves are found in this meeting or different wave systems can be occurred. What type of systems? For example, the wave height may increase when the crests combine, and flat zones may be caused when crescent uh, troughs may meet. There can be some possibility to meet two different structures of waves. When these different wave systems cross each other at an angle, the irregular wave patterns produced. They called in this case they called the cross seam. Okay, cross seam. All right. So this was the end of the fourth week. If you have any questions, you can write to the line or you can email me. You can see in the petroleumengineering.com, you will see this course as well. You can find, and also from the university's website, you can directly follow it. Okay, thanks for listening. See you next week, guys. Cheers.